Hey there, and welcome back to How'd You Get That? We are now going to tackle an exponential function problem. The problem is this: what is f of 4 when f of x passes through the points 0, 5, -3, 1027, and 1, 13/4? Now, fair warning, this problem is a little bit of a doozy, but really satisfying when we come to the solution. We won't be using any other knowledge other than the stuff that we've gone over in previous episodes, except for a little exponential manipulation. The first thing I'm going to do is write each of these coordinate points in terms of function notation. So for instance, f of 0 is equal to 5, which is equal to a times b to the 0 power plus k, or reduced down, a plus k. Next, f of -3 is equal to 1027, which is equal to a times b to the -3 power plus k. And finally, f of 1 is equal to 13/4, which is equal to a times b to the 1 power plus k, or reduced down, a times b plus k. Now all we need to do is solve for a, b, and k, and really we have a system of equations here. We have 3 unknowns and 3 equations, so we should be able to solve for each of a, b, and k. Unfortunately, however, because we have both multiplication and addition between these unknown values within our function, we can't use the simple strategies of elimination by subtraction or elimination by division, but we can still use substitution. So I'm going to take the first equation, the easiest one, and solve it for k. So k is equal to 5 minus a. I'm now going to take that value for k and plug it into the f of 1 equation. So that becomes a times b plus 5 minus a is equal to 13/4. I'm now going to solve for a. So a is equal to -7/4 times b minus 1. Lastly, I am going to plug both k and a into this last equation, the f of -3 equation. So instead of a times b to the -3 power plus k is equal to 1027, I'm going to plug in 5 minus a for k, and then substitute in again the value that we just came up for a, which is -7/4 times b minus 1. I now have a single equation, a little bit complicated here, but a single equation in terms of b. But before we move on, I'm going to clean this up a bit. I'm going to add 5 to both sides and then factor out a 7/4 on that one side. Next, I'm going to multiply both sides by 4/7. And then I'm going to combine all the fractions together. Next, I'm going to multiply both sides by b to the 3rd power in order to get rid of that negative exponent. Some things are going to cancel out here. And then lastly, I'm going to multiply both sides by b minus 1 in order to clear the fraction entirely. Last of all, I'm going to combine like terms and set everything equal to 0 to get this polynomial. So I know my value of b must satisfy this equation, but how do I solve this equation? Well, I could, for instance, use polynomial long division, which we've done in our polynomial videos and a couple of other instances. But that could take a while because the factors of 584 are numerous. It turns out that there are 16 possible factors for this polynomial long division problem. We can eliminate half of them because we know that b can't be negative, so we're left with all the positive factors here. But that still leaves us with 8 things to try, which is probably 8 too many. We can also eliminate 1 because we know b can't equal 1. However, it may be advantageous to break this down by factoring out the factor x minus 1. If we do that, we arrive at this cubic function after doing some polynomial long division. Now this cubic function is actually the crux of how we're going to solve this problem without doing too much polynomial long division. Just as b had to satisfy solutions to this quartic function, it also must satisfy solutions to this cubic function, so either one is a valid way of figuring out what b is. And though this cubic function looks more complicated than the quartic function that we were investigating a second ago, it's actually going to be useful to manipulate this cubic function to find what b is. So we're going to use some logic instead of some straight mathematics to figure this out. First, I'm going to add b squared plus b to both sides to get them away from that b cubed term. I now have this equation, but let's go back to those factors for the possible solutions to these polynomial long division problems. We can see that they're all 1 over some other number. I'm going to say that the solutions for b are always 1 over p. That must be true given what our factors are. If that's the case, then b must be less than 1. Furthermore, b squared must be less than 1. And in fact, b squared plus b must be less than 1. We can show this algebraically, but we can also just plug in our largest value for b, which is 1/2. So if I plug in 1/2, 1/2 squared is 1/4 plus b, which is 1/2, so 1/4 plus 1/2 is equal to 3/4, which is less than 1. Any p value that's greater than 2, or b that is less than 1/2, will be smaller than 1 when I add b squared plus b. So this right-hand side of the equation is always less than 1. So we're left with this inequality. 584b cubed minus 1 must be less than 1. But remember our stipulation about b, that b must be greater than 0. So b squared plus b must also be greater than 0 because b squared is going to be positive and b is also going to be positive. So that means that furthermore, 584b cubed minus 1 must also be greater than 0. So we now have these two inequalities which we can solve and find upper and lower bounds for what b must be. Now because p is an integer but b is a rational number, I am going to rewrite this as 1 over p for b instead of just b. Because I know what the powers of integers are, for instance, I know some of the powers of 2, I know some of the powers of 3, even some of the powers of 4 and 5, so that will be easier for me to compare than just saying what is b, which is some 1 over an integer value. Doing some algebraic manipulation, I find that 584 must be greater than p cubed. That's our upper bound for p cubed. What about our lower bound for p cubed? Well, doing some more algebraic manipulation with this other inequality, we get that 292 must be less than p cubed. So our lower bound for p cubed is 292. Okay, so let's go back to those factors, and particularly those p values, which remember are the denominators of each of those factors, and see which ones have cubes that are between 292 and 584. Okay, so let's just check this out. So 2 cubed is 8, which is not between those two numbers. 4 cubed is 64, which is not between those two numbers. 8 cubed is 512, which is between those two numbers. And anything greater than 8 is going to have a cube that is greater than 584. So our solution for p must be 8. And therefore b must be 1 over 8. And so we've now found our first value for this exponential problem. b is equal to 1 over 8. Fortunately, b is the toughest unknown to find in this problem. We already have an expression for a in terms of b, so if we plug in b into that formulation, we get that a is equal to 2. Simple enough. And we also have that k is a function of a, and so therefore we can plug in 2 in for a and find that k is equal to 3. So my function must be f of x is equal to 2 times 1 over 8 to the x power plus 3. But this is not the answer to our problem because the problem actually asks what is f of 4. So I can just plug in 4 for x, so f of 4 is equal to 2 times 1/8 to the 4th power plus 3. So then I get 2 over 4096 plus 3, which rounding down to the nearest 10,000th is about 3.0005. Now that was a complicated problem, but remember, if all else fails, you can always try guess and check. If you have any questions, leave them in the comments below, along with any suggestions you have for future episodes of How'd You Get That? Hit that like button, subscribe, and hit that notification bell so you never miss another math, physics, or problem-solving tutorial. Thanks so much for watching, and I'll see you in the next problem.